what we have done is we have explained how you can use this method which I just described, which is a generic method. So, if I have any fault, it does not matter what the fault is, whether it is a single stuck at fault or a bridge fault or any other fault that you can think of, they let f prime be the output of the faulty circuit and f be the output of the good circuit. Then can you apply a set of inputs A to the both the circuits? Okay. Can you apply a set of inputs which causes this to become 1? Okay. You will realize that this is a difficult problem. In the example we took, it was not so hard, right? We figured it out, right? But imagine if there are many, hundreds of inputs, okay, to the circuit, okay, then to figure out what pattern, right? So, if there are n inputs to the circuit, there can be 2 to the power n inputs possible tests. Right? There are 2 to the power n possible tests, and one of them may be able to result in f exclusive or f prime to be 1. Okay. So, this problem is sometimes called a satisfiability problem. In computer science, this is known as satisfiability. What does it mean? If I give you a circuit, right, and if I identify one of the outputs and say, hey, is there an input vector that you can apply to make this 1, right? It is like saying there is a function here, let me call this function as maybe g. So, g is a function of the inputs x1, x2, x3, xn. Okay. So, g is a combinational function or a logic function. It includes and, or, invert. Okay. So, I may have a complex function of x1 to xn, and I am saying, does there exist a way to set x1 to xn such that the output becomes 1? Okay. Does there exist a way to select x1 to xn such that g of x1 to xn becomes equal to 1? Unfortunately, there is no algorithm, so to say, okay, to find such a setting of x1 to xn. It is also possible that it is not, there is no such test vector, there is no way to set x1 to xn in such a way that g becomes 1, that is also possible. In either case, to detect whether such a thing is possible or not possible, even that is not easy. So, a brute force method, okay, what does it do? It will apply every possible input, try every possible input. Okay. See, for example, if we have 4 inputs, okay, we can try with 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, etc., etc., to 1, 1, 1, 1. Okay. So, this will result in 16 cases, and somewhere we may be able to say that 0, 0, 1, 0 seems to work, it produces a 1 at the output. Okay. But in the worst case, we may end up applying all the 2 to the power n cases. Okay, so 2 to the power n inputs combinations may have to be tried in the worst case. There is a luck factor. When we start trying, maybe in the second trial it works. Okay, but in the worst case, okay, we may end up applying all the 2 to the power n vectors. So, in other words, there is no polynomial time algorithm. Okay. We do not have a polynomial. What does it mean? See, in computer science, there are problems like sorting. Okay. So, if you want to sort n numbers, okay, there are algorithms which will do it in order n square time. That means the runtime of the algorithm is proportional to n square, okay, or it could be proportional to n log n. Okay. Similarly, if you want to search for an element, okay, I have an array and you want to find whether a particular element is present in the array or not. So, that takes in the worst case order n time. So, these are called polynomial time algorithms, okay, and they are quite efficient, right. They terminate in a reasonable amount of time. Okay. Whereas, an exponential time algorithm like this 2 to the power n, it may end up taking a lot of time. So, imagine if n is 100 or something like that, right. That number 2 to the power n is going to be huge. 2 to the power 100 is a very large number, right. So, you will realize that testing is a difficult or a hard problem. It is a hard problem. In the computer science lingo, we refer to such a problem as a hard problem. So, this satisfiability problem is a hard problem. Okay. You can try heuristic ways, you can try some algorithms like backtracking, okay, and many times they do a reasonable job. We do get a solution quickly, okay, but there is no guarantee. There may be that situation where it takes a very long time to get the solution. Okay. So, the backtracking method is a popular method, backtracking. So, what does backtracking do? It will initially set x1 to 0, let us say, and then try to see whether that works. Okay. Then if we had to make one more decision, we can try x2 to 0, x3 to 0, and let us say after trying 0 0 0 0 it did not work. So, we try to reverse, 0 is changed to 1, okay, and if that does not work, we may change to x3 to 1 and try x4 equal to 0. So, in a way it sort of, in the worst case, may end up applying every possible vector. Okay. So, backtracking is the way testing is actually solved. So, test algorithms use backtracking. Sometimes, right, they may take a very long time. Okay. Sometimes they may take a very long time. So, what the people who implement these test algorithms will do is, in such a situation, they will decide how many backtracks are allowed. Okay. They will decide that maybe 100 backtracks are allowed. Okay. If you cannot find a test vector in that 100 backtracks, they will terminate and say, sorry, I could not find a test for this particular fault. So, that is called as aborting a fault. Okay. So, in this example, suppose the test algorithm had to find a test for E bridged with F, okay. And let us say we have set a backtracking limit to 3 or something like that. So, it will try 3 different backtracks, and in that, if it could not find a test vector for the bridge fault, it will say that, sorry, this bridge fault I am not able to figure out how to test it. Okay. It will say, I am declaring that I am aborting this fault. I am, forgive me, I cannot do anything about it. Okay. So, I hope it is clear to you how tests are generated for any fault. We started talking about single stacked faults. Then we talked about bridge faults. Both of these are popular. Okay. This is the most popular model. Every industry, every semiconductor company will today use single stacked fault model. Okay. And bridge faults are also popular because some single stacked fault models, and bridge fault models, they behave differently. See, a bridge fault um, is fundamentally different from a single stacked fault, right. So, testing for bridge faults is also a common thing to do, okay. But not everybody may do that. Okay. Some companies may not follow bridge faults at all, but this is something that is quite popular. All right.